This machine learning engineer Srinivas Billa has watched Andrei Karpathy's video and ported Andrei Karpathy's GPT-2 for audio. This is a native audio. That means you can give audio input and get an audio output just based on GPT-2 architecture.
Heard what he had heard. I had seen what he had seen. And yet, from his words,
It's mind blowing. So we're going to listen to Srinivas Billa to understand how he went about it. The only disclaimer that we would like to add is this is not a perfect model. In fact, this is a model at this point is quite overfitting. But the fact that this works itself is magical, and that is why I wanted to capture these useful insights from Srinivas. Let's get into the conversation. Srinivas, thank you so much for coming on One Little Coder podcast. Can you tell us about yourself?
Thank you for reaching out. And yeah, I'm Srinivas. I work at Expedia as a machine learning scientist. And yeah, I mean, this is just like personal research I was interested in and doing. So I saw Karpathy's video, and it was very nice to follow along and build it from scratch in one file. So yeah, I just wanted to try it out.
Before even we jump into this particular project, I wanted to know what is your deep learning knowledge or background? Is it the only this video that made you do this, or you had like good background?
Yeah, I did my degree and master's at Warwick in data science. So I have a lot of background in ML and building these models, but obviously not in LLMs. I mean, that came after I graduated. So I work on LLMs at work usually. So I work in the NLP team at Expedia, and we use LLMs for a little bit. So I've been basically learning for the past year and a half or so. Yeah, and just recently I just wanted to try out different things, see how it goes. So yeah, I do have a background in ML. It's not like I came out in just from scratch.
Can you tell us about the project like GPT-2 for audio?
Yeah, so it's basically pretty much not much has changed from the code that Andrej wrote. It's just the data is different. So I think I've been interested in audio and building models for that, like text to speech and stuff like this for a long time. It's just obviously LLMs are much more popular right now. So I wanted to see if you can kind of merge it together, and especially with the launch of GPT-4o, this sort of native multimodality. And when I say native, it's not like you have an image head and an audio head and a text head, and you're kind of three different models working together. It's one singular model that's reasoning. So I want to kind of test that out and see if a model like GPT that's been used for text training work on audio. So yeah, that's where the idea came from. I think there have been some previous work, like I think Meta's Chameleon was a model where they trained on text and images. And I think another one called Byte GPT where they forget tokenization at all and go directly to bytes and train on that. And they showed it was possible to get for example, I think one of the demos really cool was they took a music sheet and then converted it into audio directly. It's just bytes, right? You can do it. But yeah, so obviously at personal research level, the scale is much smaller and you have a lot more constraints. So I want to see, okay, if I just get one singular recording, like how far can it go, right? So that was the idea.
I think the primary difference between Meta's Chameleon and your model is that your model came out. Chameleon is still paper. So yeah, can you take us
Yeah, I
through the
mean,
model and the code and the details that you have? Like, if you want to share your screen.
yeah, well, I mean, I wouldn't really count it as like a model people can use directly. Like, I think what you can think of it like um, a very big model that would just spit out a recording of Sherlock Holmes because it's so overkill on it. But yeah, I think yeah, it's just like there are so many papers, so many like interesting work. It's just that a lot of the times the model don't come out until 6 months down the line where they're trying to make it good and very perfect. But I think yeah, I think all the knowledge is there, and there are these things, and it's just you can test them out. So yeah, I'll show you the code very briefly.
While you're sharing the screen, just a curious question. While everybody's trying the same model, I mean, a lot of people have watched this video. Everybody's trying to do the same thing with text. Why did you think about doing it for audio?
It's again, it's I wanted to have but I wanted to try and train a model like GPT-4o. So I think that's the main difference right now. Like there is no model out there available apart from Byte GPT, which I'm not sure why it didn't have that much impact. But anyway, yeah, like I think in general, when people think of LLMs, they think it's a large language model, language being text. Um, but I think that's not the case entirely. Like I think we have seen multiple times, even OpenAI with Meta's Chameleon and these visual language models, they're perfectly capable of reasoning over multiple modalities. It's just that nothing has been appeared in open source yet. Well, as far as I know, there might be some I don't know about. But yeah, so and I think I was also inspired by the post from Lyle. So I'll quickly go to the post I told you. So this was about a month ago. Oh, not even a month ago. Just yeah, about a month ago. There was a post from Leon. They're like an open source not open source, but like open research people, and they showed like there have been some models before like Audio Palm that take audio and text, and they also showed a tokenizer which I used that converts audio into tokens, like a sequence of tokens. Um, and that's why I built the tokenizer on. Um, see if I explain it first, actually. So the difference between the tokenizers I use, so I use Snack, like the one they recommend. There are other tokenizers like um, Encodec, which is from Facebook, and other ones. I think what makes this different is they have this kind of like hierarchical structure where an audio is it's represented in these like coarse tokens they say, and then like goes more granular and granular. Um, and there was a video, this tutorial also linked there. But what this does is he shows that you can kind of flatten this token out into a single sequence of tokens, and you can kind of stream them out. So when you say stream them out, so you have uh, this coarse one, right? And then you take actually here. So you have the big one, you take the first and smaller one, again, you take the first, and you take these two. So you have one, two, three, four, five. I think in total there's seven because this is one. And these seven tokens become like one time step. So what you can do is kind of stream it out. So these seven become one, and then you take the next seven, and so on and so on. So that's what this code does. I took this from this video that he has a collab. I just put it into I just built a tokenizer around it. And what this does is it will take audio, convert it into these snap tokens, which is a hierarchy of coarse and then granular, and it will flatten them out into one list. And then obviously I have a function to reconstruct them as well. So yes, you have an encode, decode. Encode will pass it through the audio model, the snap model, and then flatten them out, and then the opposite for the decode. So this is probably the major change, just the tokenizer, and then everything else is practically the same. The only thing I added was a Python file to download an audio data set I downloaded from LibriVox, which is like an open domain data set. And then that will just tokenize it and for you and put it into the same format that Andrej used. So everything else part of the code is exactly the same. Nothing changes. Just some minor changes like the vocab size, because we're only caring about the audio for now. So instead of needing 50,000, it's just a smaller number, make training go a little faster. But yeah, that's mainly the changes. I talk about it a little bit in the little notes page I wrote on Medium. Yes, that's the only major difference. The tokenization, little file to do the data set, and then training inference exactly the same. I do have a collab, so anyone can go and take a different data set or anything and then run it if they want to. And yeah, as you can see, it because I used a tiny data set, it comes around 1.5 million tokens total, and it fits like so quickly and it starts overfitting. Like within 1,000 steps, you're overfitting on the training. But when I took this model at 1,000 steps, like it wasn't generating audio. But what was interesting is it learned this format of how to format the sequence in the snack style very fast. So the way the snack fonts work is you have a separator for I think in my one my file. Um, so you have a separator, like for me, I put 4097. And the reason I chose this is because the snack tokens, they have their own vocabulary size of 4096. So I added one, and that becomes a separator between each time step. So what I saw was the model learned very quickly to adhere to this format of 7 snack tokens, separator, 7 snack tokens, separator, and so on. So at this point, my tokenizer, the encode decode, was working fine, which means that the model learned how to give me the correct format. It's just the data inside, it didn't learn yet. And that's expected. Obviously, there's not enough variety of data. It's just one file. So then I'll take, okay, so I was like, that's good. But then I want to see if I train it enough, can I actually get a model that sounds realistic. And yeah, I think around 4,000, 5,000 steps, it starts overfitting to the data set, and it basically just replicates the input. But yeah, so then that's the confirmation I needed. It can basically generate infinite output that will decode into a audio that is um, actually hearable, something like that.
Just to quickly summarize, you have taken the audio file, the Sherlock Holmes, and you use the method from lines and use the method snack for tokenization. The audio
Yeah,
file goes into that, and then it gets tokenized. And now that tokenized, let's say chunks or whatever tokens, goes into Karpathy's existing code with a little bit
yeah,
modifications that you have made. And then the model gets trained. And as we can see, the model starts overfitting, which might be like good in this case, particularly because the model actually generates what is in the training data set. Is
yeah,
this correct?
yeah, exactly. So yeah, anything past 3,000, 4,000, it will just generate the data set. So it doesn't matter, like, so when you generate the notebook, um, so I start off with, so 4097 was a separator. So that's my input. So like, you know how you input a language model, you put some text and it will generate, right? So my input was just a separator. And then I wanted to see what it would generate. Um, and then, so I have a bunch of generations and they're all different. So you can sample different, but all these are just like different random parts of the model picked to generate from the training data set. Um, so like it's not like I'm influencing it anyway. It's just giving me some random lines. Um, Also, I think one note to make: I trained on a context of 2,048 tokens, and that is roughly 20 seconds of audio out. So it's like, I guess, 100 tokens equals 1 second. So let's say you wanted to generate a song like 3 minutes. Um, that would be like, I don't know, 9 times this. So let's just say 10. So you would need a 20K token context to generate 3 minutes of audio. I mean, there are some things you can do, like you can skip the last layer of this and then only take the top three, which cuts your token length down. But I saw that like sometimes if you do that, like it will degrade the air quality. So I think just keeping it as is, it's already quite optimized. Like the previous ones, uh, you need more like bit rate and you need longer tokens. I think the Snack one is actually quite good. There are other models as well. Like Snack is not the only one that can do this kind of tokenization. Um, but yeah, I think it's one of the best ones I found to do it.
And like, how long did you train and let's say compute and cost? What kind of?
Yeah. So I think I ran this like overnight on a single GPU, the I think the L4 one. So obviously this is on T4 for inference, but you can just get the L4 and then running this for like 8 9 hours, you should get a model that's overfitted to the data set and just generates quite good audio. Um, so I want to compare. So this is all well and good. Like we can get an output. So I think the next steps for me is to like build a good data set to pre-train on. I think so. I think if you go to, I don't know if he has graphs in his repo. No, he doesn't. Um, but if you've seen the graphs he's put on Twitter, you have the training data set he took from FineWeb. I think it took about uh, 10 billion yeah, 10 billion tokens. And after training for 10 billion tokens, it's actually decent. And then after 40 billions, it's quite good. So I think that's like a rough ballpark of how many tokens you need to get like some sort of decent output. So what I want to do is find 40 billion tokens of audio. So the one I took was 12 hours total, and that was like 1 million. So let's just say 1 million equals 10 hours. So if you want 40 billion or like even 10 billion, that's like 1,000 hours, right? So I need 5,000 hours of audio, of pretty decent audio, like very clean, very like no background, nothing, and also of a single voice, or maybe more voices, I don't know. Actually, that's something I want to check too. Like, if you train on multiple voices, can you like prompt it like a few shot model like of my own voice, and would it be able to um generate my voice like a zero shot voice cloning basically? That would be interesting to see as well. So yeah, if I can find some data that's good, and then obviously once you increase the data set, it means it means you need a lot more compute. So if you try run this on Colab, it will take you like weeks or months. So you need, I think when he did it, he had eight A100s on Lambda Labs, each one having 80 GB of memory. And even on that, with a 124 million model, it took him 1 hour. And then I think he also trained it for more longer to get to GPT-3 level, which took about a day. Um, so it's not too bad actually. It's only $10, so honestly, it's not too bad. It's just that you need to be able to tokenize this text, and because for text models, the tokenizer is just like very 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 fast, very quick. But in our case, it's a different model that will do it. So you also need GPUs to actually tokenize your initial input, which I think these guys did. I didn't realize they did it. They actually have a data set of um, some recordings they did, and they have the snack tokens in here. So you can probably use this to try and train. But yeah, so that's like what all my thoughts are. I mean, it's kind of just yeah, that's what I'm thinking.
Great. And if you have to say, one or couple of epiphanies that you got out of this, what would you say? Like for me personally, like the fact that this works with audio just like it worked with text itself is like, now I can probably feel that, oh, this is what Suno is doing, to maybe create music, because now you can probably pass in like musical instrument and then expect it to get you musical instruments out. Like, do you have anything that you learned out of this process?
Yeah, no, for sure, exactly what you said. Like, um, it is possible. Like before this, I thought, like, or maybe OpenAI had like a architecture change, or maybe they did something else to kind of do this like thing. But if it's just a tokenizer change and you can get decent output, then I don't see any reason for like to kind of like what is the gap, right? It's the gap is just compute at this point. Um, so I think if people do more experimentation and try and implement these solutions in papers, and actually try and build a model. I mean, it doesn't have to be good. Like for example, my one, it's not really good. It's just outputting a data set, right? But the fact that it is outputting a data set means you can do it. And if you have a model like GPT-2 even, that can do reasoning over text, audio, even images, um, it's that's a pretty decent model. Like you can fine tune it to do anything. You can fine tune it for text to speech or like the other way around. It's like one singular model to do everything, and that's what like an LM is, right? It's one single model to do all NLP tasks. It's just that we're now extending it from text to other modalities without having like a head or like a bootstrap. It's like it's natively multimodal. And I think that's what these guys from Leon also realized. Like it's not as hard as people think it is. I mean, all of the little tools are there. They just scatter around. You just need to experiment, try to fit them together and work. So yeah, I think to like kind of sum it up, I would say more more data, more compute. I think I also said it in the blog. And also, yeah, just try it out. Like it's not hard at all. Like you can train your own model on Colab for free in a couple hours. I mean, if your data set's not that big, it's fine. You can actually test it out. So like, what if? So obviously, I'm doing audio. Like, if someone else is interested, like, why don't you do video? Or like, take a 10-minute video on YouTube, like something you want to replicate. Find a tokenizer that does it for you. Like tokenize it into a sequence of text, and then just use GPT-2 or any other model really, and see if it works. And then we can think about combining them together. So yeah, it's not as out of reach, especially for small scale experiments. It's not out of reach as people think. Um, yeah, that's what I would say.
That's a really great advice. And it was going to be my second next question. That what do you want people to do? I think you have clearly summed it up. Take this, find a new modality, find the data set as small as whatever you can get that you can fit in your compute, and then train this and then see if it can work.
Yeah, exactly. I think the first step of trying to build something is to see if it works. I think you can think about it in theory. You can see like you can do all that, but empirically, if it doesn't work, then it doesn't work, and if it does, it does. Um, so yeah, I think video would be decent. I think that's basically hitting on the like the Sora or like the new um the one from Luma AI. I forgot I forgot the name. Um, which is actually quite interesting because they expect an input image, right? And then it will kind of generate the next few frames, which is basically what we did, but for audio. We input one time step, and you train for next time steps. So I think you could easily do that for video. So if someone wants to do it, then I would just say like take an hour video off YouTube, and then somehow find a way to tokenize that, and then see if you can train GPT-2 to generate that video. That'd be pretty cool if it works.
Yeah, if it works, that'll be pretty sick. And in your current case, when you're doing inference, what are you passing there? I can see the code there. It says
Yeah, so there's two things I'm passing. One is just a separator. So this is just like nothing. Just this is like putting an empty string and then asking the model to generate. So it's just, and then this one, this is a sample I took from the training data set. So I can see if the model's just, well, at this point, it should memorize it. So I think this is about 10 seconds of input audio. So what I'm testing here is if I say, the quick brown fox, I want the models to say jumps over the lazy dog. So that's this example. But obviously I'd use Sherlock. So this is what one line from Sherlock. And if you do this and it does work, you can come and see the samples, and they should match with the initial training data set. Yeah, but it is quite slow though, especially on Colab. I think this also I took from Karpathy's code. This it doesn't have like all of the stuff like from VLLM to kind of make things go fast. It's just a simple one to see it. As you can see, it took us about like 5-10 minutes to generate 20 seconds of audio.
and
Yeah, actually, I was going to say, and one more thing. Obviously, I took GPT-2. GPT-2 is quite old by now. There is like Llama 2, 3. Even more recent architectures like Mamba, um, training stuff on that as well would be a good way to see and test as well.
Are you planning to test it with let's say new architectures like SSM like Mamba?
Yeah, I think the people from Cartesia AI,
Yeah,
I think that they
yeah,
said that they
yeah,
used a Mamba type of model to train their text-to-speech model, right?
yeah,
And it's
yeah.
much faster and I can't remember where the graph is, but there was a graph of comparing the same data on transformers versus Mamba, and for audio specifically, it was way better. Um, so yes, I think that would be a pretty interesting thing to try as well. Like take the exact same data set here and try replicate it on the Mamba and see if it like trains quicker or um, yeah, stuff like that. That would be interesting as well.
Great. And given that you use LLMs at your work, and also you're like hobbyist hacker at residence, what is something that excites you about let's say LLMs and what we have currently?
Um, I think the efficiency side of things, like I think just recently I saw this to a post on someone running Mixtral on their OnePlus phone, and that's crazy. Like I think a couple of months ago we were struggling to run Mixtral on my MacBook, like has 30 GB of RAM, and I was running like Quant 3. But the fact that you can run it on a phone now, and obviously the recent announcements from Apple and Google, like where they have these models running locally, especially Gemini. I think that's multimodal. It's just that they haven't released that one, um, and that running locally. So I think going forward, and we keep seeing these things come lower and lower, and to inference. I think it'll be very nice if you can see it for training as well. Like maybe like a couple of years from now, you'll be able to train GPT-4 on your on your laptop, which is would be crazy to think about right now. But I think if people still find ways to make things more efficient, that'll be pretty cool to see.
And is there any open source project that that inspires you, like makes you replicate that kind of a open source project?
Yeah, actually, that's it's called MapMol free LLM. It's
Yeah,
very recent.
yeah,
Um, I think this builds on the earlier LLMs are in one bit from I think it was from Microsoft
it
where
was from Microsoft. Yeah.
yeah where they replaced the weights with integers or not integers even just like 1 0 -1 like you say and then they show that you can get exactly the same performance um, with this. So I think training on this would be decent to try as well, especially like because the code's ready and you can train um, and it fits into like Hugging Face like normal. Um, and they even have pre-trained models. So like this, I think they showed like it uses like 4 to 8 times less memory when optimized. So that's crazy. That's like basically if you can run Mixtral now, then you can run um, like Mixtral times 8. Like if you train it on the same size, obviously. But yeah, again, it's the issue is compute and not enough people have it really. So and even if you wanted to buy it, it's very expensive. So I think yeah, right now the major constraint is compute.
Yeah, I think probably if this project takes off, Nvidia shares might go down. So we never know because people wouldn't need that many GPU, and you can do a lot of things with CPU if you
Oh no,
want.
like no, I think the opposite. Like if you
Oh,
can do this, then people will just scale it up even more. So
okay.
right now, like the maximum we see is 50 billion, 70 billion, right? Because that's like the limit of local compute. If it goes 8 times down, then you will see like 1 trillion parameter models running locally, which I think we have seen like so far. Like we're pretty sure you scale models up, you get more performance. I mean, that's just a scaling laws. You need more data, more parameters, better performance. Like even now, like if you can run 70 billion locally, why would you run 7 billion if this is better performance? So if this works, then unless maybe people like optimize it for CPU, but even then, I'm pretty sure if this works, then you would just train bigger models locally rather than trying to go smaller.
That is great. And thank you so much, Srinivas, for sharing all your
Yeah.
insights. How can people follow you? Where can people follow you?
Yeah, I mean, I post everything on Twitter. So that's probably where I would go. Or like on LinkedIn, you can give me a follow, or even like message me if you have any ideas, like stuff like that. And also, if you know where I can find some GPUs, that would be good as well. So yeah,
Yeah, thank you so much. And we'll share all the links in the description for people to follow you. Thank you very much for sharing your
yeah.
knowledge.
Thank you. Thank you for inviting me as well.
Thank you.